one more time. So I'm going to give a series of lectures on the way how to implement qubits in different types of technologies. So I was doing this research on the quantum computation for the last 2 years, and some of seminars will be devoted to this topic. So let me first come back to this idea of superconducting qubit. So last week we have such idea of Josephson junction. So basically we have a superconductor 1, superconductor 2, and there is some insulator in between. And the system, and we send certain current in the system, and this current was supposed to have two components. One was current of superconducting current plus normal current. And in superconducting currents, it's a current of Cooper pairs, and essentially we have a situation where this current of Cooper pairs is simply this non-dissipative current. So we can write it now in such a form. So basically we have the current of Cooper pairs. So there is a phi, this is phase difference between first and second superconductors. So we have two wave functions, macroscopic wave functions, so psi2, psi1, and each of these wave function can be parameterized by some amplitude and phase. So basically we have situation like here. And this phase difference is nothing else as phase of first superconductor, first wave function and second wave function. And so I simply denote it as phi. So this is so that there is superconducting current plus there is a normal current, which stands for voltage over resistance plus displacement current that flows via a superconductor. So essentially we have such situation as Q over VC, which leads to formula that current is C dV over dt. So we have situation as here, and here we have a capacitance. So this is our superconducting current and normal current. Normal current means current of electrons that are not Cooper pairs. They are not. They are subjected to Fermi statistics. And then quite recently we have explained that we have a superconducting current this is so-called DC Josephson effect, and then we have an AC Josephson effect. In AC Josephson effect, voltage is across junction is proportional to dynamics of phase difference. This is this. So basically, we are going to obtain the following equation that was also obtained last time. So the total current can be written in terms of phase difference across Josephson junction. So we have 1 over R, H over E. This equation will have a structure of non-harmonic oscillator with a damping. So essentially we have such equation as here. So here this is this damping curve. So everything here is described by this, the whole dynamics of Josephson junction in RCSJ model is described by this equation. This is RCSJ model. This is not very but still refers to a phase difference in macroscopic wave function. And now, if you have any remarks, please put some remarks on the chat. All right, so, and now there was a nice trick that we did last time. The trick was that we can go into Hamiltonian description of the system. We can introduce the idea of washboard potential. So at first, I make this assumption that this is constant, total current is constant. And initially, so I can write it in the whole equation in the following way. I can multiply by such factor. I will explain its meaning later. So here it is. Over h over 2i. H I. And here we have such equation. So because we have no dissipation, I will place resistance going to infinity, which will correspond to this term. So we can recognize that such equation can be obtained in such a way that d over dt is of this form plus maybe that way is 0 cosine t. And then we have 1 over 2 h over 2i. And then there is this term dt over dt squared. So clearly we have such equation. So, and then we can claim that everything what is in the brackets is set to constant Hamiltonian. Therefore, I will introduce Hamiltonian H0. So I will call everything that is inside is H0, and H0 is set to constant. So basically what we have is that we have formulated that during our equations of motion, such Hamiltonian is preserved. And now what happens is that such Hamiltonian is preserved. We can put some extra constants. Let's say h, some other Hamiltonian. So basically this Hamiltonian is constant. So this is very important observation. And now we identify that this guy is nothing else as some nonlinear potential, and this guy is nothing else as some constant times canonical momentum square. So this is our Hamiltonian. So and then that way. And then what turns out is that this momentum is proportional to this phase difference velocity. So this is our proportionality, and then this guy corresponds to our position in harmonic oscillator. This one corresponds to some velocity or okay. And then there is idea how to go deeper into quantum equations of motion, because what you see here is that simply you can make such nice picture. Maybe I will place it in that way. So here's a phase difference. There is some Hamiltonian, and if we forget about this dynamic term, so maybe this is like UV. So we have essentially we have such so-called washboard potential. So this is very important because here the energy levels will leave in our Josephson junction system, but we have to come into that. And going from a class, so this is still a kind of semi-classical picture. What happens is that we have to replace this scalar with operator, and again this phase difference with operator phase difference. And as you know from harmonic oscillator, we have famous commutation relation that is basically like this. So H pi is, so that's like this. And also you know that one of representation of position operator is as this, and one of representation of momentum is H over I, V over dx. So this is what we will try to think in that way. So one of the suggestions would be that that simply this operator is like this, and then that our phase momentum could be written in such a way. This is one of the possibilities. And this will lead us to interesting picture. So, so since then we could express Hamiltonian in terms of this operators, and then we simply come into equations of motions, quantum equations of motion. All right, so let me move on. So basically, you know that we have our quantum system dynamics that's in such a way. Maybe now I will switch to some presentations done by some students that will give us this picture in greater detail. 1 second, please. So I have to. Yes. So. Yeah. All right. So let me make a screen sharing, and share is. Yeah. All right. I hope it's visible to everybody. And now I will make a full screen. So basically we have, this is what we already discussed. There are DC and AC Josephson effect. So this is DC Josephson effect. And now we come into a description of some physical systems. My particular, so before I was mostly describing types of systems that was flux qubit that is superconducting qubit that is controlled by a magnetic flux, and also I describe phase qubit, a qubit that is controlled by electric current. Now I want to describe another type of qubit that is Cooper-Haber box, and I want to do it in greater detail. So basically, what is the system? So okay. So the flux qubit was, we have a closed loop of superconductor. There was Josephson junction. There was external solenoid, and there was a magnetic field that punched via this interior of this loop. This was flux qubit, and also okay. So now I go into this Cooper pair box. So what is the essential in Cooper pair box description is that maybe and we will move to one more time to this sharing of this screen with camera. And so let me, yeah, so essentially the central feature is that we have a small superconducting island, and so how is now the system that is of our top interest? So we have a small superconducting island. We have this isolator, and then we have another bigger superconductor. And there is a possibility for a jump of Cooper pairs. So one Cooper pair is jumping from one side to another side. And in such case, there is also condensator, so plate condensator with some charge. So essentially we have voltage to be applied here. And this is our quantum system in our description. So we can parameterize this. There's certain number of electrons, in this small island, and our quantum wave function will be like this. That this will be the case of a sum of n from minus infinity to plus infinity. So we have En. This is our wave function. Yeah. So, and of course, this wave function is normalized. So essentially, this leads to the condition for these coefficients. That some of these coefficients must be set to 1, and this is from minus infinity to plus infinity, right? And then we need to describe the Hamiltonian. So before, the Hamiltonian was described by a phase. Now it's more suitable to describe Hamiltonian by number of Cooper pairs in this small superconducting island, and we have certain parameterizing voltage Vg. So what will be the Hamiltonian? There will be energy of electric field and energy of Cooper and energy of Josephson effect. So I'm going to express now the Hamiltonian for the system. So basically I will use certain spectral representation of this Hamiltonian. So I will have such case as given here. So there will be some charge and energy, and this will be n minus mg. And then this will be written in such a way, minus AJ. And now there is this Josephson effect plus in that way. So what we can recognize here is that there is exchange of particles. Actually, this is 1/2. So there is some exchange of particles between this system and this system. This is Josephson effect. So there's Josephson energy and charging energy. In principle, there's also supposed to be a magnetic field energy, but this energy of magnetic field is it's quite negligible since this is on jump of a single Cooper pair, but still formally it can be counted. So in this simplistic approach, as given here, the energy of this Cooper of magnetic field is omitted and later it will be recovered. Okay. So now we have a Hamiltonian, and there are two parameters to describe this system. So before, you remember, there was a picture of phase and phase change with time, and now this was such a representation. And now we have a representation of number of Cooper pairs, and there will be change of these Cooper pairs. So actually, formally, we will have such operator. So this is like corresponding to our position, and this is like corresponding to our momentum, and quite clearly we have this type of relation that I operate. So basically we have this relation that has to be fulfilled, which simply turns that this operator is going to be n, and this operator, this momentum, is going to be n. So this is quite useful. And okay, so now how to write the Hamiltonian for such a system. So obviously we have, so this is Josephson energy, and this is charging energy. It's important to admit that we have here Vg, that is polarizing voltage. We are talking about very small voltages in the range of millivolts, and basically what is important is that so that Ng maybe here, Ng is a proportional to Vg, this polarizing voltage. So it's like kind of so this is quite important feature in this model. And then we have simple Josephson two-level system, and obviously we can write infinite matrix. This will be diagonal terms, and those terms will be on diagonal. So basically you can write it AC, say -1 minus Eg squared, and on the diagonal we can write it AC minus Mj. And then obviously we have this term that is going to be here, and then we have this Josephson interaction term, over half, and again we have here and from here. We have zeros. So all our are zeros. So this is our Hamiltonian matrix representation. So obviously this is, we have only three lines that are not zero. So this is our Hamiltonian. So if you want now to attempt the existence of energetic levels, well, sure you can do it, but we are limit ourselves to a very simple system. So let me just write it on the charging n minus mg square minus aj over 2 aj, and here we have mj square. This is our minimalistic level Hamiltonian. And then the rest is simply just algebra. So we can describe its eigenenergies. So simply we have the equation for eigenenergies. Minus E. Yeah, so that's this will lead us to the quadratic equation. And this quadratic equation has two solutions for eigenenergies. So it's kind of textbook issue. Maybe I will show some real solutions. So let me move on. Yeah, so I will. Yeah, perhaps I will. Okay. Change screen sharing. Yeah. Yeah, so this is what we've done so far, such type of analysis. And so we have our Cooper pair box, now our charging energy and energy of Josephson effect. And this is our Hamiltonian. And then charging energy is parameterized by a charge of Cooper pair 2E over 2C, some capacitance. Then there's some threshold number of charges that exist due to non-zero polarizing voltage. And there is characteristic Josephson energy that is connected with a superconducting order parameter as it is given here. And of course, this matrix, which I have just shown, is of such structure as given here. So this cosine of phase difference was expressed in such type of representation, and there was Hamiltonian in that way. Okay, and and then solving this equation, we will get eigenenergies, and these eigenenergies can be controlled by polarizing voltage that is proportional to Ng, and so we can tune this this landscape of energies. For us, so it's basically that we can obtain this is basically this idea that we have this tuning by Ng, and there are, again, as you see, there's ground level and excited level, and this will be used to encode the qubit. Usually, this qubit is in dilution refrigerator at I don't know 30 millikelvin. So this idea comes from 1998, and this was a qubit that have quite much charge noise, and however, it was the first. So this was, in a sense, a kind of single electron device, since the Cooper pair was used, a pair of two electrons that have opposite spin, and this phenomena obviously is only taking place in superconductors and in Josephson junctions. So there's also interesting to see that every jump of electron is inducing certain phase difference. So it's shown here that jump of electron is equivalent to existing current. And as you know from previous considerations, existing current is imposing phase difference. So, so that's quite an interesting feature of this effect. This scheme of Josephson effect and implementation of quantum information is very important for most common quantum hardware systems that are based on so-called transmont superconducting qubit. And I'm going now to describe this transmont superconducting qubit in greater detail. So basically, now we move to the case where we have two parallel single electron devices, and so we write it as here, and then what happens is that we use external magnetic fields to control it. I try to find the picture of the structure, but it's not depicted in greater detail here. So basically, maybe I will switch screen for a while and just try to come back to this camera so I can draw this structure in greater detail. Okay. I just need to see. Okay. Yeah, so one second. So basically, so how to implement this double superconducting islands? That's a very important question. And so essentially, yeah, well, I'm not sure if my camera is visible. Try to recover. Yeah. All right. So what is the situation? The situation is that we take small superconducting island 1, which was bigger than before, and we placed two insulators here and here, and then we place one bigger part of superconductor, and then we make such again, voltage bias. Voltage bias, again, there is a plate, there's charge plate, and this is SC2. There is insulator, and so we have a hooping of Cooper bars here and here. So essentially from a electrical point of view, we have there's a closed loop of superconducting. So actually, we can have also external solenoids with a current flow. There's solenoid. In this solenoid field, there is a magnetic field that is going to punch this Cooper pair box. So here we have a current control. So this is magnetic field control. And there is voltage control. There are two electric and magnetic field is involved in the control of the system. So essentially, we write it as essentially as this. Then there is two Cooper pair box involved. And there is voltage control, and there is a phase, magnetic flux phase, that is magnetic field phase. There is integer of magnetic flux, and so this is H over 2I. And here it's integer number. So this was quite and this is nothing else as a transmon superconducting qubit. So basically, we have you remember we have superconducting qubit architectures. It was phase qubit. So basically, we have Josephson junction, and we send a current via Josephson junction. And this is as this. So there's current control, flux qubit, it was a superconducting ring that was interacted in one way by insulator, and simply there was a solenoid in its proximity, and it was only controlled purely by magnetic field. Then there was a third, and there was a Cooper pair box qubit. So actually it was like, you remember, it was just described. So there was a big metal plate, there was polarization of voltage in G, and then there was a small superconducting island, insulator, and superconducting island. So this was Cooper box, and this is 4-1 transmon, and transmon is used in IBM quantum experience. So whenever you have a chance to log to the computer, to IBM quantum computer, you are going to use this arrays of qubits. I think commercially available are this like 20-30 qubits on one chip. There are certain operations implemented. All right, so let's